Hey chemists, welcome to another exciting lesson for our acid and base unit. This is one of my favorite lessons because we're finally getting to talk about pH, which I know is a term many of you have heard prior to this class, and you may know a little bit about the pH scale, but what we're going to do is we're going to dig a little bit deeper into what that really means. Let's go ahead and take a look. So what I have here and what I think is really fascinating is that pH can be used to explain, or pH is actually very important rather in a lot of gardening. And I was always really fascinated as a child with my mother's hydrangea plants because they were so different from the hydrangea plants that my neighbor had. And what was different was the color. So my mom had these beautiful pink hydrangeas in her yard, but my neighbor had these bluish hydrangeas in her yard. So I was always curious as a child, where did the different flower colors come from? And I obviously assumed that they were just different hydrangea plants. But when I started to dig a little bit deeper, I actually learned that the color of the hydrangea is based on the pH of the soil in which it's growing. So here you can see that my neighbor's pH in her yard was somewhere probably around a 4.5, and my mom's was more around a 7. So what is pH and what does it really represent? Well, pH has kind of a lengthy definition. So I'm going to give you the lengthy definition and then I'm going to give you the shortcut understanding here. So the definition of pH is that it is a figure, a numerical figure that is used to represent, represent the acidity, or we don't call it basicity for bases, we call it the alkalinity, so the acidity or the alkalinity of a solution, and so pH literally stands for power of hydronium. So we're really measuring how much hydronium is there in solution. Now, obviously, some other things that you may know about pH, that it's on a scale of 0 to 14. If it's lower pHs, that means it's more acidic. If it's higher pHs, that means that it is more basic. These are just some things that you may have previously known before this class. All right, now, before we dig a little bit more into pH, I want to just quickly talk a little bit about Arrhenius acid-base theory, and we're going to actually tie in Le Chatelier's principle to this. So based on the Arrhenius theory, how do we define an acid and how do we define a base? Well, remember, Arrhenius is the theory that is going to rely heavily on the H and OH production in solution. So if I have an acid, that means that I am producing H plus or H3O plus. Remember, we use those interchangeably, producers. These produce H plus or H3O plus in solution. If I have a base, then that means that I need to produce OH minus or hydroxide solutions, or ions in solution. Now, acids, H plus, H3O plus, base, OH minus. We've talked about something that's acidic. We talked about something that's basic. What about something that's neutral, right? And the first thing that always comes to mind is water. Water is really a neutral substance. So why is water neutral? Let's try to think about this in terms of Arrhenius theory. Now, if we think about the chemical formula of water, water's chemical formula is H2O. And if we think about what that would break apart into, H2O breaks apart into H plus and OH minus ions, So note that we have our H plus ions from our acid, our OH minus ions from our bases, And so notice that we have equal parts H plus, we have equal parts OH minus, So our concentration, our water is neutral because we have equal concentrations of H plus ions and equal concentration of OH minus ion. Remember, those hard brackets represent concentration. Now, when we have those equal amounts, equal H plus, equal OH, they balance each other out. Our pH is equal to 7, okay? So it's very simple to see why water would be neutral. We have the equal parts of H plus and OH, but what happens when we start to add either acids or bases into our water solution? So let's first take a look at adding a base into our solution. So I actually want to start this out with just rewriting my equilibrium because, again, like I said, we're going to use Le Chatelier's principle today. So H2O, okay, is in equilibrium with the H plus and the OH minus ions, okay? And what happens to the equilibrium when I dissolve NaOH into solution? Now, notice that in our chemical formula, we don't actually see NaOH in the equilibrium equation. So when we say that we're dissolving NaOH into solution, what we're really referring to as adding Na plus ions, but more importantly, OH minus ions, because remember, NaOH is ionic, it dissociates, it breaks apart into Na ions and OH ions, okay? So when I add NaOH into solution, note that we're really talking about the addition of OH minus. So if I add OH minus, remember, if we add, we shift away. That means that our equilibrium will shift towards the left. Okay, so adding NaOH shifts the equilibrium to the left. Okay, and what's going to happen? Really, okay, yeah, we're going to produce more water, but I'm actually, again, mainly interested in the H plus. Remember, pH is going to be all about power of hydrogen. So how does this impact the amount of hydrogen that I have in solution? Okay, and so as we shift to the left, remember that everything that this arrow points to increases, everything it points away from decreases. And so what I really want us to take away from this is understanding that as I add OH, it actually causes my H plus to decrease in solution. So what does that mean now? We used to have equal parts of OH and H plus, but now that we've disturbed that, which one do we have a greater concentration of? OH minus or H plus? Since our H plus is being depleted, our concentration of OH is now greater than our concentration of H plus, okay? Now, what do you think that means about our pH level, okay? If I have more OH, then do you think that this is acidic or do you think that this is basic, okay? Increased amounts of OH with lowered amounts of H plus means that our pH is going to be greater than 7. It is going to be a basic solution. All right, let's do this again. Let's now talk about adding an acid and how that impacts our solution. So again, I just want to quickly rewrite my equilibrium. H2O is in equilibrium with H plus and OH minus, okay? And so what's going to happen when I add HCl into solution? Now, again, as I'm adding HCl into solution, that's really the same thing as adding H plus and Cl minus ions into solution. And so we're really talking about this H plus ion, okay? I add H plus into my solution, that causes the equilibrium to shift left, okay? So as HCl is added, okay, equilibrium shifts left, okay, and as a result of that, our H2O production increases and we use up that OH minus. So how does that impact our once equal balance of ions? Which one do I have more of now? Which has a greater concentration? Okay, the concentration of our H plus is now greater than the concentration of our OH minus. Okay, and as a result of that, what's going to happen to our pH? We're going to have more H plus present, and therefore our pH is going to lean towards the acid side, or lower than 7. Okay, we are going to have an acidic solution or a decreased pH. Okay, so I wanted to do that whole process just to have you, or to kind of introduce you to a deeper understanding of what's really happening in this water solution as we're adding these acids or bases into solution. It's disturbing our equilibrium. We're using up our H plus, or using up our OH minus, and creating an acidic or basic solution. Now, how do we calculate pH? Okay, how do we determine pH values? Now, this is a logarithm-based mathematical calculation, or a log-based calculation. This is something that typically as freshmen you're not super familiar with, so I am going to take a really quick amount of time to go over logarithms with you, and then we'll dig into pH. So what is a logarithm? It's kind of the most ridiculous mathematical explanation here, or definition, but it is essentially how many of one number do we multiply to get to another number, okay? And that sounds ridiculous, and without showing you an example, I don't think you know what I'll mean. So here's an example, okay? Let's say I gave you the problem log base 3, meaning down here, this little number is a 3, log base 3 of 81. Okay, what is the answer to this? Now, you might be looking at this and saying, what do you mean? What is a log? So when you see a log base whatever number you have to another number, what you want to do is, I would recommend rewriting your problem in this way. What this is really asking is 3 to what exponent is equal to 81. Okay, so 3 times 3 gives us 9, times 3 gives us 27, times 3 gives us 81. So how many times did I have to do that? I had to do that 4 times. So the correct answer here is 4. Now, what's really beautiful about pH is that we're not going to be using log base 3, log base 4, log base 5. All of the log calculations that we use in this class are log base 10, and that's called the common log. Okay, so common log is log base 10. All right, we don't really write it as log base 10 because it is considered the common log, so we really just write it as log. Okay, so our problem here that I want to give you is log of 100 equals what? Okay, again, let's rewrite that. Okay, so again, common log is a base 10, so this is asking us 10 to what value, okay, is equal to 100, okay? And so 10 times 10 is 100, so that's log, that would be a 2 as our answer, okay? So let's go ahead and solve the following log problems, okay? Log of 0.01, log of 0.01. So this is really saying the same thing as 10 to the x equals 0.01. Now, this is a little weird because if you notice, in order to get to a value that's less than 1, we're no longer working in positives, we're working in negatives. So 10 to what value gets us to a 0.1, okay? And the answer is that it's going to be -2, right? Okay, so our log here would be -2. What about for our next problem? Again, this is really saying 10 to the x equals 0.00001. Okay, and this is going to give us log 10 to the negative 5 is going to give us this value. Now, these values that you see here are actually representative of two concentrations of hydronium ions, okay? So these values right here, let me put them in this yellow, these values represent hydronium concentrations, or the concentrations of H+. That doesn't show up, but it's whatever. So my question is, if I was actually calculating the concentration of H+, I should be getting my pH value, but these values are coming out negative, and we don't have negative pHs. So how can I correct this? The official mathematical calculation to calculate pH is going to be represented by pH equals negative log, okay, of the concentration of H3O plus. Okay, now what's nice is that you can just punch this into a calculator. Okay, it's very simple. There's a log button. You just hit the negative, the log, and then you put in your 0.000 whatever. Okay, but there's also a shortcut, and I'm going to teach you that shortcut right now. Okay, so when you get these concentration values, they are always going to be less than 1. They're always going to be 0.000 something or other. Okay, and lucky for us being in Regents level chemistry, they're always going to be in the powers of 10. So they're going to be 0.01, 0.001, 0.0001, so on and so forth. So when you get these concentrations, in order to complete the shortcut or to do the shortcut, what I would recommend doing is actually going ahead and placing these in scientific notation. So to rewrite this value in scientific notation, I am going to get 1.0 times 10 to the negative 2, okay? Then I'm going to get here for this one, okay, 1.0 times 10 to the negative 5, okay? Now, looking at these scientific notations, okay, and the calculated pH values that you got, how are these two things similar? Notice that we have the exact same value as our exponent equal to our pH. But what we do need to do is we need to make these positive values. So if you get this negative 2, that's the same thing as saying 2. If you get a negative 5, that's the same thing as saying 5, okay? So compare the calculated pH values to the scientific notation you had written. How are these two similar? Okay, the exponents, okay, actually I want to get rid of that, and I want to just say instead pH is equal to the absolute value of the exponent of the concentration in scientific notation. All right, this video is getting really long. I'm so sorry. I'm going to pause here. We're going to take a look at practicing this shortcut method in class, and we'll also go over the remainder of this sheet in class on Monday. Have a great weekend, guys. Thank you guys so much.